here we go. This is lecture chapter 4. It's going to be 4.1, the history of the atom. We are studying atomic structure for this chapter. The history of the atom starts way back with Democritus in 450 BC, who, against the thoughts of the prevailing philosopher Aristotle, there we go. Democritus thought that all matter was finitely divisible into invisible particles that he calls atomos. And atomos is Greek for invisible. And all of his followers were called atomists. Okay? Now, Aristotle did not agree with this because Aristotle thought that all particles were infinitely divisible. That's ugly. Infinitely divisible. So that whenever you take something, you could divide it and divide it again and divide it again and divide it again, that you could keep doing that forever. And Democritus felt that there was a smallest particle that could be representative of anything that you were dividing. And so a loaf of bread would have a smallest particle of loaf of bread that would still be bread. And then if you were to divide it again, then it would no longer be bread. And this was really the first idea of the atom. Okay, the theory continued to build when Lavoisier, a French tax collector and scientist, discovered by running an experiment in a closed system, he discovered the law of conservation of matter. Now, this concept was very fine and dandy from a experimental standpoint, where you were able to figure out that what you had to begin with was all there when you finished with, but we weren't quite sure why until John Dalton comes along with his atomic theory of matter. His name is John Dalton. Okay, John Dalton was an English school teacher. He didn't teach English, he was just from England, who was looking for the reason why air dissolved in water. Now, this is where his theory was really groundbreaking, is these four statements. This is atomic theory. All known elements are composed of atoms. Atoms are hard, extremely small, unbreakable spheres. Okay, so you can already see how atoms are unbreakable spheres are very similar to Democritus's idea of atom. However, this word right here, element, really took its true meaning under Dalton's theory. Atoms of the same kind of element are alike in all ways. So no matter where the atom is, or no matter what it is, how it is used, every atom is exactly the same. So there's only one kind of gold atom. You can't have a pretty gold atom and an ugly gold atom. They're exactly the same. Atoms are not altered or changed by chemical reactions. The chemical reactions don't do anything to the atoms themselves. And atoms of the same element combine in different ratios to form compounds. For example, hydrogen and oxygen can combine to make H2O, and they can also combine to make H2O2, which is peroxide, which if you see a very, very bleached blonde person, they may have some familiarity with that. Okay, this is an important thing for you to summarize in your notes. Okay, you need to be able to explain Dalton's theory and the importances of it. And I'll tell you that part of the importance of the idea of element is Dalton created the chemical alphabet. Before, with Democritus, every individual thing had its own atom, had its own atomos. And so this loaf of bread was different from this loaf of bread, which was different from, a different thing. And each thing had its own representative particle. And so there would have been billions and billions and billions of individual particles that would have represented its own nature of the particle. Now, Dalton says there are only so many elements in the universe. And each element has its own atom, but the atoms themselves combine in a multitude of ways to create everything that we see. And this is very similar to how the English alphabet has 26 letters, but there are millions and millions of words in the English language. Same thing with chemistry. There are only 90 naturally occurring elements on Earth, and they combine in a multitude of ways to make the millions and millions and billions of substances that we are aware of. Now, an atom is only so big. The radii of most atoms fall within the range of 2 times 10 to the negative 11th meters to 5 times 10 to the negative 11th meters, or 810 million cubic atoms, or 8.10 times 10 to the negative 8th, or positive 8th. Copper atoms can fit across the diameter of a penny. That's huge. And even though they're very, very small, we're actually able to see individual atoms with a scanning tunneling microscope, which fires electrons at a particular atom and bounces back, and we can image the atom from there. So that is section 4.1. That is sufficient for you to complete lecture chapter review 4.1, and we will see you guys next time. This is P-Dog signing off.